So this will be a quick video discussing the optimality of A star. In A star search, we will be prioritizing all of our nodes in our frontiers by an estimate of how much it will cost to get from the initial state to the goal through that node. So that's this f function that consists of the g and the h functions, where the g is the cost to get from the initial state to n, and h is the heuristic estimate of the cost to get from n to the goal. And when the heuristic is admissible, then A star search becomes optimal in tree search situations, where admissibility is defined as just being an underestimate. The h of n is always an underestimate of the actual cost it will take to get to the closest goal. And in graphs, if the heuristic is consistent, which is defined by this equation on the right, the bottom right, then A star search becomes optimal. And there's some tricky things that happen in the graph search setting that we'll talk about a little bit at the end of this video. But first, let's think about the tree situation, where it's a little bit easier to think about. So in this case, we're just going to consider admissibility. So we're going to try to understand why admissibility is enough to guarantee that we're always going to find the least expensive goal state. So if we look at A star in a tree, let's consider first, let's just look at the whole expansion and frontier building process. So consider the fact that let's say we're in the search tree and we've expanded state A. So we're looking at state A. So we look at the children of state A and we see that we have B and C, and we now want to add B and C to the frontier. And the scores we want to add these nodes with are their estimate of the path to the goal through them. So we do that by looking at g of b plus h of b and g of c plus h of c. So that actually is going to look like this. So what we're going to add to the frontier b with the score that's going to be the cost that it takes to get to b, which is going to be the cost from s to a, then the cost from a to b. And then add the heuristic at b. And then c is going to be the cost from s to a and the cost from a to c plus the heuristic to c. So these are the two pieces. This is g of n and h of n. So there's a really nice property about these components when we look at trees, which is that because trees have only one path between the root of the tree and any node in the tree, g of n is always the exact cost of the only path to n. Right? Think about it this way. As the search algorithm is walking around the search space, whenever it expands a node, it will have seen the full path to get from the root to that node. And it can just add up the costs along the way, and it does this with a recurrence. But it can add it up along the way and know the exact cost it's going to take to get from S to B and from S to C. So that's a bit of good news, that we're not going to make any mistakes when we're trying to estimate the G part of the equation. Now, when we think about admissibility and the heuristics, remember the property of admissibility says that h of n is an underestimate of the cost to the goal. So with those concepts in mind, let's now think about the scenario where we finally discover a goal and we're about to expand it. So consider the fact that we just visited C and we expanded its children, and among its children we saw this goal state that's called G1 on the bottom right, and let's say for the sake of argument it is actually the best possible goal state. And then considering or continuing this argument, we also have another goal state. There's another goal state that exists someplace in the search space that you get to through B. So it's in the subtree of B, and we're calling that G2. So the question we want to ask ourselves about optimality is, could we ever have chosen G1 to expand and therefore exit the search program if G2 was actually cheaper to get to? Right? If it was actually cheaper to go to G2 instead of G1, could we have expanded G1? So a couple of things to note when we ask ourselves this question is the fact that in the frontier, G1 will be added with what will be exactly the true cost to G1. Right? The reason for that is that it's the score that we give for G1 is going to be all the costs along the path that the search algorithm has explored to get to G1, plus the heuristic estimate for G1, which we can pretty much assume is 0. Right? Admissibility actually tells us it's 0. So its score, its priority queue score is going to be exactly the cost to get to G1. And then going back to what we saw previously, the cost for B, for node B in the priority queue, is going to be an underestimate of the true cost to get to the goal through B. So what that means is if G2 were actually cheaper than G1, then B's underestimate of the cost to get to G2 would be even smaller, would be even cheaper than the true cost to get to G1. So this is really just an example. You can abstract away from this and try to come up with a general principle, and eventually you'll just lead yourself to the full proof of this argument. But my rough intuition is as follows: it's that if we want these two properties to hold, and the first property is that the priority of each node that we expand, whenever we expand a node from the priority queue or from the frontier, that node's score is always an underestimate of the true cost to the goal through the node. So admissibility gives this to us. The second property is that the priorities of any goal state that we expand is going to be the true cost to the path to the goal. And what that means, when you have these two properties, what that tells us is that when we, by analogy, go shopping for the next state to expand, we're always going to have the option of, either purchasing a goal state for its actual price or trying out an intermediate state for an underestimate of its actual price. So the result of that analogy is that we're always going to try out all the cheaper options before we ever get to the true best goal state. So maybe you can come up with a better analogy, but I think this attempts to get a better, clearer picture of how admissibility plays a role in this type of thing. So with that said, we can now think a little bit about graph search and how things get a little bit different. So in graph search, remember the problem is that as the search algorithm explores the graph of search states, it has to consider, or it has to handle the fact that it may be able to find alternate paths to the same nodes. So for example, on the right, here's a very simple diamond graph. Let's say you start at the start state, and when you go to the start state, you find its neighbors, and you add that to the frontier. So you add A and B to the frontier. And then without loss of generality, let's say in the next stage, it expands A. So it looks at A, and it discovers a new neighbor, C, a new node that it didn't know about, so it adds C to the frontier. So then let's just say, for the sake of this example, that the next node that it expands is B. So when it expands B, it will also see node C again. It will discover node C again. And what could go wrong in some ways is that we may add C to the frontier twice. And it turns out that's actually not so bad. But the bigger concern is when we think about not just adding nodes to the frontier, but adding nodes with their priorities to the frontier. So the problem is, in this example, we went from S to A, and then we went to C, or we discovered C and added it to the frontier. And implicitly in what I just said there is that we added C through A. We added C with a path through A and the associated cost of the path through A into the frontier. So then what can go wrong, what you could imagine going wrong, is that you then go to node B, expand node B, and discover that C is one of B's neighbors, but you don't add it to the frontier because you say, oh, it's already in the frontier. But the path from S to B to C might be cheaper than the path from S to A to C. So we initially added a more expensive path to C than we have available to us. So there's two solutions to this. And the first is what the textbook suggests for uniform cost search, which is that when you encounter a child node that's already in the frontier, you just update the priority of the child if you found a better score. right? And so in the previous example, if you discover C again, but you've discovered that you can get to C faster through B, then you update the priority of C, and that's fine. That's not too bad. The downside of that is not too many. Well, there are data structures that support updating priorities, but data structures that don't support priorities are a lot simpler. So a second solution is to allow multiple copies of the nodes in the frontier, but when you select nodes from the frontier, you just ignore nodes that you've already visited. So we would essentially add 2 copies of C. In the previous example, you would add 2 copies of C to the frontier, and then when you go to expand it, you would expand the cheaper one, and then later on, if you pop C off of the frontier again, you just move on and pop the next node off of the frontier. So with all that said, what that means is that during the process of adding nodes to the frontier, we may temporarily add nodes to the frontier that have overestimated costs, right? Because if we reach that node through a path that's not the optimal path to get to that node. But we will never expand a node unless we have actually found the true shortest path to that node. And this is not the full picture. This is not enough to prove that consistency is enough to bias optimality, but it points out a subtlety that helps our thinking when we want to reason about this argument. And I certainly haven't proven to you the last bullet point here. I'm just saying that this is a consequence of this procedure, or of either of these two solutions for the problem. So there's a lot to think about here, and as I have mentioned to you previously, if you want to see the textbook proof, it's right in the textbook on page 95 of the Norvig-Russell book. But for me, I'm still searching for a nice intuition, at least something as clear as the case for tree search, that gives me intuitive confidence that A star is optimal, aside from the fact that lots of smart people before have written down verified proofs of its optimality. We can look at these proofs and figure out and understand each step-by-step claim, but at least for me, I don't come away from those exercises with a great, off the top of my head intuition. So let's continue discussing this over the next few classes, and maybe we'll come up with something.